Hello, welcome to the lecture 17 of the course Transportation Network Analysis. So, in the last class we were discussing about genetic algorithms, so we will continue in that direction. So, let us take a look at different crossover methods. So, until now we had looked at 2-point crossover where 2 points are randomly selected for a pair of strings, and between those points the strings are swapped. Okay, so for example, suppose we have these two parent strings P1 and P2 here, and suppose these are the 2 points around which we decide to do crossover. So here you can see that this portion 1 0 has now come here in this offspring string, and this portion 0 1 has come here. Okay. Everywhere else the string remains the same, that is, this portion is still the same as this is same as this is same as this, and so on. Okay, so this is a 2-point crossover. Now you can try to think that there can be variations of different crossover methods. For example, if you just do crossover around 1 point, it is called 1-point crossover or a single point crossover. So here 1 point is randomly selected for a pair of strings, and the strings are swapped around that point. Okay. So for example, suppose we randomly select this point around which we want to do the crossover. So then this portion gets to the bottom and this portion will get at the top in the new offsprings. Okay, so these are the two offsprings that you get after doing this single point crossover. Now the single point crossover is one extreme end of the crossover types. Another different category of crossover is called uniform crossover. So here at every bit point we flip an unbiased coin, and depending on the outcome of the coin we swap that bit position. Okay. So here now we will be flipping a coin for every position here. Okay, so there are 6 bits here, so we will be tossing the coin 6 times. So for example, suppose we tossed a coin and this is what we get for the first bit position, then we get tails, then heads, and tails. Okay. So for the places where we got heads, so there we will be swapping the 2 bits in the parent strings here. So you can take a look at this, that the first position, the 4th and the 5th, here we are swapping these bits. Okay. And for the remaining bit positions we do not swap. So these are the 2 offsprings that we get here. Now an automatic question that arises in the mind is that there are these different crossover methods we have seen, so which one to use? Now there is no straightforward answer here. It depends upon what is our priority. For example, if computation time is our top priority, so then single point crossover will take the least time, because then the crossover has to just happen around 1 point. Whereas this uniform crossover will take the largest computation time, because here we will be checking for every bit that is possible, and in average case almost half of the bit places will get swapped. Okay. So this uniform crossover leads to very dense crossover, in the sense that it is very rich, that it allows a lot of bits to get swapped, but then it is computationally very high. So that is why depending upon what is our priority, we can decide what kind of crossover method we want to select. If you want to balance between computation and the richness with which we do the crossover, so then 2-point crossover might be kind of a balance, because it is coming in the middle somewhere. Okay, so let us move on now. So now we will be seeing how to solve the travelling salesman problem, TSP, using genetic algorithm. So until now we had only seen how to solve Max-1 problem using genetic algorithm. Max-1 problem was very trivial problem for which we already knew what the optimal solution will be. But TSP is a non-trivial optimization problem. So we will be seeing how to solve that, and in this process we will be seeing that now we can no longer use the same representation of genetic algorithm that we were doing until now. So we will be learning a few new concepts as well. So if you recall, in travelling salesman problem we start from a given place and we have to visit a set of given places and we have to come back to the starting place in minimum time, or we have to cover minimum distance. Okay. So, suppose that we have to travel these 8 places and we have to come back to the starting place. So, the question is, in which order should we go from one city to the other? So, the type of genetic algorithm that we will be using to solve this traveling salesman problem, this will be called ordered based GA, because here things are different from the regular representation of genetic algorithm that we have seen until now, because until now the order in which the bits appeared, now it will matter. For example, let us take a look at 2 example solutions of the traveling salesman problem. So, this is one solution here. So, here this node 3, suppose we start from Jodhpur, then we go to Kolkata, then we go to Coimbatore and so on. So, we will be going to these different nodes and then we will be coming back to the first one. Okay. So, here the order in which we go matters, okay, which did not matter in the case of the Max-1 problem. For example, in the Max-1 problem, if we had a total n bit positions, for example, if there are 10 bits and suppose we have a string where there are 6 ones, okay. So, then the bit positions where these ones are does not matter as long as we have 6 ones, okay. But that is not the case here. So, here what node will come after node 3 will matter, okay. So, here node 5 coming after 3 is not the same as node 7 say coming after 3, okay. So, that is why this representation of strings is different from what we have seen until now, okay. So, this is the first solution, this is another example of second solution, okay. Now, here I am not specifying what should be the population size that you should take, because there is no exact number that is applicable for all the problems. It will depend upon problem to problem, it will also depend upon what size of problem we are solving, okay. So, for example, there is a trade off here. So, if we take very large population size, then the computation time will be very high, whereas if we take very small population size, then we might not be able to explore the solution set properly. So, that is why there has to be a trade off, and what is the right population size to choose in any problem while we are solving genetic algorithm depends upon the experiments we do and so on, okay. So, right now we are not focusing on how to select the population size, that gets understood as we solve different kind of problems. One thing is that you should not be setting the population size to be almost equal to the number of feasible solutions, because if that is the case, then if we are anyway generating the number of strings that are equal to the number of feasible solutions, we might just as well enumerate all of these solutions and then find the optimal one, okay. So, that is why the population size should be much smaller than that, but it should not be too small so that the genetic algorithm is not able to explore it properly. So, in genetic algorithm, once we define the randomized population, so then the next thing to do is to do selection, and before we are able to do selection, we need to define the fitness function, okay. So, the fitness function in this traveling salesman problem needs to be defined in a slightly different way, because TSP is a minimization problem. We are trying to minimize the length of the tour that we obtain. So, that is why we cannot set the fitness function to be equal to say the length of the tour that we get, because by intuition we understand that higher is the fitness of a string, the better the solution is, okay. So, that is why if x is the length of the tour of a solution, then for that string we will be setting the fitness function to be equal to 1 by x. So, that smaller is the length of the tour, the better the fitness of the corresponding string, okay. Now, note that here we do not have binary strings, but we have ordered strings. So, we will be seeing that we cannot apply the same crossover and mutation methods that we saw before, okay. But before that, let me tell you that the selection method, the philosophy behind the selection follows in the same way here, because while we are doing selection, the only thing that matters is the fitness of different strings, and we have already defined how to calculate the fitness of a string in the case of TSP problem, okay. So, that's why we are not discussing how to do selection here, because you can either use Rowlett wheel selection that we have discussed before, or we can use K-tournament selection method. Whichever one we want to use, we can use. There is no change here as compared to what we have seen before. Okay, but things change regarding crossover and mutation. Okay, so for example, suppose we have to do crossover between these two strings in the TSP. Okay, and suppose we have decided to do 2-point crossover, and these are the 2 points around which we want to do crossover. Okay, now if we do crossover in the traditional sense that we have seen until now, so then we will be getting these two strings, because here 2 3 will come in this new string and 7 6 will come here. Okay, but then there is an issue, because you can see that in this string 7 is, for example, coming twice, 6 is also coming twice, whereas nodes like 2 and 3 are not coming at all. Similarly here, node 2 and node 3 are coming twice, but node 6 and 7 are not coming at all. So these are not feasible solution of the TSP problem, because we want that in the TSP every node should be visited exactly once. Okay, so that's why we cannot do the same crossover approach that we have seen until now. So that's why we will be introducing a new crossover operator called order 1 crossover. So let us see what it means. So in order 1 crossover, a swath of consecutive bits from parent 1 drops down, and remaining values are placed in the child in the order which they appear in parent 2. Okay, so let us understand this through an example. Suppose this is one parent string that we have. Okay, and this is the second parent string. We want to do crossover. So the first thing that we can do is that we can arbitrarily pick any two positions. Suppose we pick these two positions. Okay, so this part of the string 7 to 1 6 will come as it is in the first child string or the first offspring string, and now we still have 4 more places to fill here. So in order to do that, we need to look at how do these numbers 3, 5, 4 and 8, which are yet to come in this first child string, in which order do they come in the parent string. Okay, so remember we have to yet to put 3, 4, 5 and 8. Okay, so let us start going in this direction in parent 2. So the first string that we encounter is 5 here out of 3, 4, 5 and 8. So we will put 5 here. Then we encounter 8, so that is why we put 8 here. Then we encounter 3, so we put 3 here, and then we encounter 4, so we put 4 here. Okay, so this is the way we have obtained the first offspring string or the child string. Okay, so you can see here, while generating this string, we use information from both the parents. This part of the string came exactly as it is, as it came in the parent 1, whereas the remaining bits came in the same order in which they appear in parent 2. Okay, so now in a similar way we can generate the second child string also, or the second offspring string also. So now what we will be doing is that we will be considering parent 2 to be on the top of parent 1. Okay, and then we will be putting the remaining bits in the same order in which they appear in parent 1. Okay, so let us see how it works. So this portion 7, 6, 8, 1 is put as it is from parent 2. Now we are yet to put 2, 3, 4 and 5. Okay, so let us look at in which order they appear in parent 1. So 3 comes first, so that is why 3 has come here, then 5, 5, then 2, 2 has come here, and then 4 here, and then 4 here. Okay, so in this way we can generate the second child string also. Okay, so let us now move towards mutation here. So mutation involves now reordering of the list here. Recall that in the previous examples, what we used to do mutation is that we used to go bit by bit, and we used to flip a coin. Depending on the outcome of the coin, we used to flip the value of that position or that bit. Okay, but that was possible because we only had two choices there, 0, 1. Okay, and there were no constraints that there has to be exactly these many times the 1 has to appear in the string or 0 has to appear in the string and so on. But that is not the case with TSP. Okay, so we cannot do this kind of flipping here. Let us take a look at this through example. So instead of that, what we will be doing is that we will be randomly exchanging the positions of two chosen bits which we pick arbitrarily. So suppose we have picked 7 and 6 here, okay, so we just swap them. So while doing this, we can see that still 6 is exactly coming once in the string and 7 exactly coming once in the string that we have got, okay. And you can also see that why the previous mutation method that we had discussed would not be applicable here, because if we would have gone suppose bit by bit here, suppose we go to the first position here, now suppose we flip a coin and the outcome is such that we should do mutation here. So the first question is that what we'll replace this value with, because there are 7 other alternatives, and the thing is that if you replace it with 5 with some other value, suppose with 4, then 4 is already present here. So then it will come twice and 5 will not be appearing at all in this new string. So that's why we have this new kind of mutation method where we are randomly exchanging the positions of 2 bits that are chosen arbitrarily. Okay. So this is a graph which is showing how does the solution of traveling salesman evolves as some iterations pass. So this has been obtained when someone had solved this genetic algorithm to find the solution of traveling salesman. So here this is the picture for this iteration 20 here. So you can see that there is this tour which is shown here, its total length is this here, and as the iterations increase, so now it is iteration 90 here, and you can see that the tour has become smaller now as it is less dense, the length has also decreased, and similarly the length has decreased further as the iteration number has increased. So this is how things will kind of likely evolve as we solve the traveling salesman problem using genetic algorithm. And one question also comes in mind, when to stop in genetic algorithms. So for that also we have discussed various termination criteria. One termination criteria can be that we stop when we reach a maximum number of predefined iterations, or when we see that there is no change in the best solution that we are obtaining, or we see that the average fitness value is not increasing significantly, and so on. Okay. So genetic algorithm has a lot of applications. It is used in a lot of places where we require control of some equipment, like for example if you have to do missile launching, missile evasion, aircraft design. It's also used in communication networks. It's also used to find solutions of various games. It can be used for trajectory planning and so on. Okay. So genetic algorithm, since it is not using any particular problem structure to solve the problem, so that's why it is a meta heuristic and it's applicable for a wide variety of problems. And this concept of genetic algorithms is easy to understand because it is based on the concept of evolution. So that's why it's very advantageous. And one more benefit that genetic algorithm offers is that the classical methods of optimization may easily get stuck in local optimum, okay, and the solution may depend a lot on the initial solution. Okay, so what do we mean by this? So there are various methods for solving different optimization problems. There are some problems usually start with an initial solution, then in some way they go to the next solution, then the next solution, and so on. So in that way, how we started in the beginning determines where we will finally reach, because those kind of algorithms are deterministic. A related example can be taken from the iterated tour partitioning. So there, when we were finding the solution of the vehicle routing problem, we had started with a tour of traveling salesman problem. So depending upon how good that tour is in the beginning, it will determine how good solutions we obtain for the vehicle routing problem. Okay, and since these classical methods for optimization approach mostly in deterministic way, and they make many times decisions which are best for the current iteration. For example, if you take a look at the savings algorithm, there we were going down in the savings list. So we were first trying to place that edge, that is we were trying to connect those nodes that will offer the highest savings, and we'll go to the next pair of nodes and so on, given that they satisfy some conditions. So in that way we are going greedily, that is we are doing that decision that gives us the best benefit in the local sense, that is what we think will be the best in that iteration. Okay, but while doing all of that, there is no guarantee that we'll always reach the global optimum. Sometimes we can get stuck to local optimum also. Many of these algorithms such as Dijkstra's algorithm, Prim's algorithm, Kruskal's algorithm are also greedy in approach. For example, in the Dijkstra's algorithm, whenever we had to select the next current node, we were selecting that node that had the least tentative distance and so on. Okay, and very few of these algorithms that we've discussed until now will offer guarantees on how close they provide the solutions as compared to the optimal solutions. In some cases, when we are lucky, for example, the shortest path problem, the minimum spanning tree problem and so on, so they can be solved in polynomial time. So for them we have these polynomial time algorithms that will give you optimal solutions. Dijkstra's algorithm, Prim's algorithm, Kruskal's algorithm, all of them solve these problems in polynomial time and they are guaranteed to give optimal solutions. But for some problems that may not be the case. Okay, for example, we have these saving set algorithm, iterative tour partitioning algorithm and so on. So those are also greedy in nature, that is they try to make the best decisions in the given current iteration, but they are not guaranteed to be optimal. Okay, so that's why these classical methods of optimization can get stuck in local optimum, which is usually not the case with genetic algorithm, because it first operates on a set of solutions every time. That is, we have a population and all of these operators like selection, mutation, crossover are randomized, and because of presence of operators such as mutation, these introduce diversity in the solution. So even if the whole set of population of a genetic algorithm say proceeds in a particular region of the feasible area, because of the presence of mutation it will introduce some changes, and because of that there is a likelihood that we can get some solutions which are different and they are belonging to a different area of the feasible region, and that might prevent this whole solution getting stuck to local optimum. Okay, so it allows the search to become more diversified in the feasible area. Okay, because of the presence of crossover, mutation and so on. Okay, so GAs usually do not get stuck in local optimum that easily, and since we have a whole set of solutions that are generated in the beginning, so therefore we are not depending on one initial solution. Okay, so that is, these are one of the major advantages of genetic algorithms, and genetic algorithms also support multi-objective optimization. So we have not seen examples of this kind of optimization until now. So these optimization methods usually have more than one objective functions. For example, suppose instead of the shortest path problem we want to find that path which offers short time also, but then we want to increase the familiarity also. Okay, so now a path may not always be the shortest and might not be the most familiar one. So in that cases, what kind of solutions should we find which are good in both the sense? Okay, so those kind of problems are multi-objective problems, and genetic algorithms are very well suited for solving these kind of optimization problems. Okay, so with this we will be ending this discussion here. Thank you.